this Friday we'll have a midterm review session from 2 to 4, right? And we're booking the room. So once the room is booked, we'll let everyone know. And I guess that maybe some people might have conflict. So probably we'll arrange another review session next week. But this week will be a Friday afternoon. Okay. And the grades and the statistics are out, and I guess it just means that yeah, please do review the course materials, the slides, and the textbooks before exams, right? And so they are important. And yeah, let me think. Okay, so we'll see that in the end, I think there will be some curbing at the end of the semester, but I hope that people do not rely on that we're going to do curbing, and so yeah, don't count on that, right? So try to learn about the lecture content a bit more, right? So review the materials before exams, okay? And use the office hours. I think I do realize that ask the TAs. I do realize that not many students are using the PSO session as a TA office hours, right? And so go to these sessions, right? And also the office hour we have every week, like before this lecture, right? In my office, we also have a office hours, right? So use these office hours if you have anything that you feel you don't know, right? You don't understand about the lecture content. Okay. All right. So now let's continue with file system. Right, so we'll do a quick recap, right? So we start from how a file is organized on the disk. Right? Historically, right, in the very beginning, there's a very simple organization of file, right? And this is very straightforward and have many disadvantages. Okay, we'll start with the simplest file allocation strategy. Right? You have one disk, and this disk is organized as a big array. Right? You have many blocks. This is the first block. This is the second block. Right? So these blocks are organized in an array. And so every file, when you allocate storage space for a file, you just allocate some piece of data in this array. Right? In this example, the first file is allocated at the beginning of the disk. Right? So this is start, this is length, and that's it. Right? So the entire file is allocated at the beginning of the disk. And then the next file will start from the end of the first file. Right? So continuous allocation. Start from the end of the first file, and then the next file will again start from the end of the second file. This is called continuous allocation. Okay? And the downside, right? So what is the downside? I think the downside is, we mentioned it, right? So you need to know the size of the file, right? Start and length, and it cannot be dynamically adjusted, right? So if you, after you allocate a file, later you want to modify it, like appending more data to this file, you cannot do it, right? Because its length is fixed. Okay, but right after it, there is another file, so you cannot simply just allocate more, adjust the length of this file. Okay. All right. Another downside is that fragmentation, right? So once you finish using a file and you deallocate its storage space, you have holes in this disk array, and they cannot be easily reallocated. You can imagine that maybe this file size is 1 megabytes. Right? After you freed it, you have 1 megabyte free space in the storage. Right? But when you allocate the next file that you want to allocate has let's say 1 gigabytes. Right? It's a very huge file, and then this 1 megabytes cannot be reused for this new file, right? Because before it and after it there are other files. You don't have one continuous space for this new file, even though you have a lot of small free spaces over the entire disk. Okay, fragmentation, right? Similar to memory fragmentation. We have discussed this. Okay, but interestingly, right? So continuous allocation have many downsides, but interestingly, the adapted version of continuous allocation is very widely adopted. So has anyone heard about the log structured file system? Right, so it's used everywhere. So do you want to explain it? How does it look like?
Basically, like when you allocate a new extent, you just append it to the end of the disk.
Right. So you have you keep appending, right? So it's continuous allocation, but you keep appending, right? Maybe the file in the beginning has 1 megabytes, but it will have when you want to grow that file, you append another maybe 1 megabyte block at the end of the at the beginning of the free space, right? So and then you modify the pointer in the first file. The last block of the first file will have a pointer to the next block, right? So that's how you later we'll see, right? So that's a log structure file system, and that is very widely adopted in SSDs and also in cloud systems. Okay. All right. So this idea is very simple, but it has many downsides. Okay. Linked list allocation. So we have a directory, and in this directory you have a file, and you have the address to the first block of this file, and then this first block, once at the end of this block, there is an pointer to the next block in this file, okay, and so on. Right? So they are organized in the linked list. Okay, the downside is that because these blocks are on disk, and the pointers, right? Remember this, every block contains a pointer to the next block, right? Because the pointers are also on disk. So if you want to traverse this list to find maybe the 10th block of your file, you really need to load the first 10 blocks of this file. Right? You need to load them one by one and traverse this linked list. Right? This is very slow, right? So loading a block from disk is very slow. Okay, that's a major downside. You can have a linked list, but traversing linked list is very slow if this linked list is stored on disk. Okay. So the next optimization is that we want to avoid storing this linked list on disk. Right? So let's make it a very small linked list that you can store in memory. Okay, very similar to Xenu's linked list. Right? So this is how very similar to how Xenu maintains linked list in its table data structure. Okay. You have a very small table data structure that organizes this linked list, and then you can store this table inside the memory. So you know the linked list that belong to each file, and this linked list is in memory. So if you want to access the 10th block of file 1, you just traverse. You still need to traverse this linked list, but all the linked list, the nodes of the linked list is in memory. Okay. So you can quickly traverse the linked list, get the address of the 10th block, and then use that address to access disk and specifically, right, only load the 10th block of this file. You don't need to load all the previous block 1 to block 9. You do not need to load them. You only need to load the 10th block. Okay, so this is the idea to store the linked list table in memory. And then after that, so we further improve. So this linked list can be huge. If you have a very large disk, right, terabytes of data, or for example here, even if you have a small disk that only has 20 gigabytes of storage space, you have 80 megabytes. You need 80 megabytes to store the linked list. Okay, and this is a very small disk, right? Because nowadays everyone's storage is huge, right? 1 terabyte, 2 terabytes, you can have that amount of disk storage in your computer. Right? So, right, so this is 80 megabytes, right? And let's see if you have let's see 1 terabyte of memory, then it's about 50 times, right? 50 times that's 4 gigabytes. You need 4 gigabytes of memory to store all the linked lists. That's too much. So the next idea, right, called index allocation or allocation using inode, is that we do not want to store this huge table in memory. We want to split this table into smaller tables, and we only load the small tables on demand. Right? So we want to avoid a huge table and only load small tables. How do we do that? Right? So for every file, the idea is essentially we split this big table according to files. Every file has its own linked list organized in a small table. Right? If a file is not used, we don't load its linked list from disk. Right? This linked list can stay on disk. Right? Only for the files that we are actively using, we load their table into memory. And that's the idea of index allocation. Right? Because you can imagine, right, on your computer, how many files are there? Right? Numerous files are there on your computer. Right? But how many files are you actively using? Very few of them. Okay, so that is the point. Right? So every file maintains its own small table, and only the files that are actively used by the user, their table will be loaded into memory, and this table is organized in a data structure called inode. So these names are fancy, inode, index node, or but it's essentially a small table that is used to represent the linked list of data blocks for a file. Okay, yeah. So if you really think about these techniques in OS, right? So virtual memory, file system, you can see the core idea is not that complicated. So virtual memory is essentially a map. Right? You use a map to map virtual memory to physical memory. Right? And file system is how you organize a linked list. Right? How you organize linked list in memory. Okay, and but making them efficient, right? Making these data structures work efficiently in OS, that is very, very challenging. Decades of work, of effort is spent on this. Okay. All right. So yeah, let's look at the detail again of inode. Okay. So inode again, it is representing the linked list of or the table of data blocks belonging to one file. Okay, so in this case, this is a table. Right? The first entry of the table represents the metadata of a file, right? Who created this file, who owned this file, what's the last access time for this file, what is the privilege of this file, etc. Okay, and the second, starting from the second entry, that is pointing to the data blocks that belong to one file. Right, the first address points to the first data block of a file. The second address points to the second data block of the file. Okay, and then until here, it becomes similar to a linked list, and starting from that single indirect, double indirect, and triple indirect, right, starting from here. What does a single indirect mean? What is an indirect block? I think we explained it last lecture. Right? What is an indirect block? Compare indirect block and data block. What is their difference? We explained last lecture.
The data block directly contains the file contents, while the indirect block will contain the address to the data block which contains the file's contents.
Exactly. Right. So the data blocks contain the file contents, part of the file contents. The indirect block contains addresses to the file content. That's single indirect. Double indirect contains addresses to blocks that contains addresses to data blocks. Right. And similarly, triple indirect has 3 indirections. Okay, and and this is why I'm not sure whether you have tried to create very big files on your own computer. Because if you have tried, you might know that there is a limit of the file size. And this is the reason that the file that you can create in a Linux OS, right, has a limit of the file size. So single indirect, double indirect, triple indirect, if you use up all of them, right, if somehow you have a huge file that uses up all of them, then that's it, right? So you cannot create a file larger than this size. Okay, but usually this size is much larger than the disk that you can have. So it's rarely, you can rarely create a file that's larger than this size. Okay. Yeah. So this is like a linked list, similar to a linked list, but it's not. So it has limited size. All right. Okay. Why do you actually? Why do you not use a linked list? Why do we want an inode? Random access. Right? If I want to get a tensor block, I just directly use the start of the address of this block and add 10 entries, shift 10 entries, and get the address of the 10th block. Compared to if you really use a linked list, you need to follow the linked list one by one, and that will take time. Okay. All right. Yeah, I'm actually not sure whether you have noticed. So I think this is another interesting lesson to discuss when it comes to design real-world systems. Right? So you can see that ideally, right? So if you have linked list, it can grow infinitely. It feels that that is a good feature to have. Right? But in reality, the data structure that's really used in mature systems, they typically sacrifice this kind of property. They don't want to support infinite growth of the file, and they treat that kind of property for performance. We don't use linked list, we use this kind of table structure where you can quickly, or array-like structure, right? And so you can have a much faster random access, and this optimizes the performance of your computer significantly. But these design decisions have to be made very cautiously. Right? So, for example, here they provide this triple indirect so that in reality you rarely can create a file, can have a file that is larger than this limit. Okay. Yeah. I think that's another lesson that you can learn from the design of OS. Right? It's not always preferred to have a perfect data structure if the this perfect data structure has a disadvantage in its performance. Okay. All right. So this is a calculation of how much data that you can use. The limit of the file size. Directed blocks only 10 KB and a single indirect 256 and a double indirect 64 megabytes and triple indirect. I didn't do the calculation. Maybe you can try to do it. It's a huge amount of storage size. You can rarely create file larger than that. Okay. All right. So that is how a file is organized on disk. Its core data structure is conceptually a list of blocks. Although it's organized using this special data structure called inodes, but conceptually you can think of it as a linked list of blocks. Okay. And that is about how files belong to, so how blocks belong to each file are organized. But what about the remaining blocks that do not belong to any file? Okay, that is called free blocks. How are they organized? Okay. Right, so they are also they are all organized similar to what you have learned about memory organization. Right? In Xenu, the free memories, they are organized in a free memory list. And similarly, free disk space is also organized in a list of free blocks. Okay. This is the simplest way to organize the blocks. There is another approach called bitmap. Right? So bitmap is actually more often used in real-world OS. Do you know what is a bitmap? Can you imagine how a bitmap is used to organize a free list, free blocks? What is a bitmap? You can imagine that it's like an array, and every item in the array is 1 bit. You can think of it like that. Okay, and what is the meaning? Right? What does each bit in this bitmap represent? Right? That's a question. How that answers how a bitmap can be used to organize the free blocks. Yes.
If you have n blocks, then you can have like n bits that represent 1 bit for each block, and then if like the bit is 0, then it can mean either that it's free or it's not free, and then 1 opposite.
Right. That's a gist of it. Right? So you have a bitmap, and 0 represents this. If the first bit, if the first bit is 0, it means that the first block is not used by anyone. It's free. Right? If a bit is 1, it means that this corresponding block is used by some file, although it does not know, right? Because if you really want to know which file this block belongs to, you need more than 1 bit recorded information. That's too much. Right? And so you only use 0 and 1 to represent whether a block is free or not free. Right? So that is the bitmap. Okay. In Linux, usually if you use Linux supported file system, and usually this is how they represent free blocks. You have a bitmap for each disk. Okay. All right. Yeah. So yeah, to just compare these two approaches, right? If you have a free block list, right? So the entries of other block addresses that are free. So you need to have these addresses in the block contents, and the last entry points to another block, right? So you will have to have this entry in the block content. Okay, one block links to another. Okay, the pros and cons, right? It can be large, it can be stored on 3 blocks, it can load 1 block into memory at a time. So this is again, right? This is similar to the downside that we discussed previously, where you organize the data block or file using linked list. Right? Because this approach is essentially saying that similarly, we organize the data, the free blocks in a linked list. It will encounter the exactly same challenges as organizing the data blocks of each file in a linked list. Right? So this is just to see that. Okay. Right. So this is this calculation is to see that, okay, if you want to store this linked list, how much blocks you need to record this linked list of free blocks. Okay. Similar challenge. Right? So to avoid that, use free bitmap. Right? So every bit represents 1 block. Right? Yeah, 1 is free, 0 is not free. Sorry, I think I used them reversely. Okay, and right, so if you have 16 gigabytes free, and every block is one size is 1 KB, and you use 1 bit per entry, then you only need 2,000 blocks, right? Much smaller than the previous number, right? This is 65,000 blocks. Now you only need 2,000 blocks. It's orders of magnitude smaller. Okay. And also it's fixed in size, so you can always put this free bitmap at the beginning of the disk. Okay. So that is how free blocks are organized. Now, directory. I remember we mentioned that the file system is organized from a user's perspective. The file system is organized in a tree structure, where the internal nodes are directories and the leaves are files. And so we discussed how files, right, regular files are organized on disk. So they have a list of data blocks. Each data block stores the content of a file. For example, if you have a text file, then the data block stores the text belong to your file. What about directory? A directory is very different. What about directory? What is the difference between a directory and a regular file, and how is it used to support this tree structure file system? Right. Now think about this. Right. So I'll give you a minute to think about this. The answer is hinted here, but I'll give you a minute to think about it. Right. How is a directory used to support this tree structure? One second. Right. Just let everyone think about it. So the essence of a regular file is it's a linked list of data blocks. What is the essence of a directory? I think we'll get whoever raised their hand first. Right? I think that the guy raised their hand first. Okay, I think enough time. I think you raise your hand first, then you can answer. Not yet. Okay. Okay. Anyone else?
I was gonna say maybe it's like a linked list of file names.
Linked list of file names. That's good guess. Right? That's very close. Right. Anyone else?
It is a linked list to the inodes.
Linked list of inodes. That's also very close. It also is actually a combination of your two answers. So it's a linked list of linked list of data blocks, and the content of data block is a map, and maps file name to inodes. That is the essence of a directory, right? Forget about forget about the linked list of data blocks. Right? The essence of a directory is a map, which maps a file name to its inode. Right? Because inode contains the meta information of the data blocks belong to this file. Right? So file name to inode mapping. Directory essentially is a map. It stores file name to inode mapping. Okay? And it stores its file name to inode mapping in its data blocks, right? Because again, its directory is just as a regular file. It has a list of data blocks. The difference is that in directories data block, it stores its map. In other files, their data block store whatever content. For example, for text file, it stores text. For a media file, for a movie file, it stores the video. Right? The difference is the content. Okay. Let me see. Okay. Right. So let's go through this process, right? And to understand how a file system is, this data structure of a file system is used, right, to provide its service. Okay, so this is opening a file, user Bob file, right? So it goes through this sequence of operations. Right? I'll give you a couple minutes, right? So we'll see whether someone can explain this. So think about this. Right? If you understand this entire process, how these data structure that we mentioned were used, then you understand how file system works. Okay. It might need you to imagine, because some of the fetch root directory, we did not explain where is a root directory stored. Look up user, right? You need to imagine a little bit how it's done. But if you can explain this step by step, then you know how file system works. Yes?
So is the lookup always O1? Can't we like make a hash map or something and make it O1? Or
Sorry, can you say again?
is the lookup always O1 if you are looking for a file in a
Oh yeah, it's scanning the data blocks, right, of a directory.
But can't we like make a hash map or a try to make it a bit faster?
Yeah, you can. I think if you look at the file system, the real world file system, I think they might have this kind of optimization. Alright, so couple minutes. Try to explain this step by step, right? If you can explain it step by step, you know how file system works. Okay, I'll give you one more minute, and then we'll see whether anyone can try to explain this. Okay, anyone want to give it a try? So it's okay if you got stuck in the middle, right? So any number of steps if you can explain.
So basically we'll start by finding the user, and then we'll go through the user's inode. We'll get user's inode, and we'll go through the inode to find out all the addresses to the other inodes it has, and one of those addresses will be called Bob, and we'll go to Bob and retrieve its inode, and then do the same process again to find the inode for the file, and then get the inode for so it is a name to inode kind of magic.
Yeah, that's very close. That's very close. So just a few clarifications. Right? Let's go through it step by step so that you understand how this works. So the first step, root directory. So how do you know, right? So how is the first step performed? Root directory, hard coded. Right? Root directory is hard coded. Hard coded for each disk. When you initialize, for example, if you have a fresh disk, you need to initialize it, format it. Right? And when you format it, the root directory is created. And it's always in the same place. And then you mount this formatted disk to your computer. If anyone has used the mount command, when you mount it to your computer, you are essentially loading the inode of this root directory. Sorry. Okay, so root directory is always there, and you can directly find it. It's hard coded. And then, given the root directory, you will grab the data blocks belong to this root directory. Why is that? Because the root directory, again, is a directory, so it's a map. It stores this map in its data blocks. Right? It stores this map from file name to files inode in its data blocks. That's why when you fetch root directory, right, you get its inode and use its inode to grab its data blocks. Because the map is stored in the data blocks. And when you scan the root directory's data blocks, you will see that in this data block, it stores this map from file name to inode, and one of the entry is a map entry from user to user's inode. One of the entries from user, this user file directory, it has an inode, right, to its inode. Okay, so that's lookup. That's what the second step is. You scan the data blocks belonging to root directory, find the entry that represents the mapping from a user, this file name, to user files inode. That's how we do this lookup. Okay. Now, once you finish lookup, you already know the mapping and you get the inode. You know the address of the inode belonging to user file, and then you use this inode to retrieve the blocks for this user directory. What is stored in this user directory's data blocks? What is stored in this user directory's data blocks?
Mapping with file names.
Right, again, right, the same thing, right? The mapping between file names to inodes, right? Which one of the entry has this mapping from Bob to Bob's inode. Okay, that's what is done here. Right? Lookup Bob, right? Scanning through the data blocks belonging to the user directory, and in the data blocks you will find a mapping from file name Bob to this Bob's inode. So get Bob's inode. Okay, and then you repeat. Right? You use Bob's inode. It's again a directory to grab its data blocks, and in the data block you will find the mapping from this file to files inode, and then you can really access the content of this file. Okay. And so if you have executed, for example, CAT, right, cat, you use cat, this give it this absolute path of this file, right, cat, this path, then underlying what happens is this process. Okay, it traverses the directory tree, right, like this, eventually gets an inode of file, and then starts reloading the file's data block and printing the content of the file to your console. Right. If you use cat with this file name, underlying this is what happens. Okay. All right. Yeah. So I think this is this process, right? So when you are reviewing a file system, this process is the key, right? If you feel that you cannot explain this yourself, then it means that there might be some blind spot in your understanding of how file system works, right? You can use this as an example to verify your understanding of file system. Right? It's a very good example. Okay. Directory representation and hard disks. Right. So we already mentioned that a directory is a file that contains a list of entries, right? And each entry is a pair of file name and inode. Okay. So in this case, every pair is called a hard link. File name to inode number, a hard link. So you can tell that because it's a pair of file name to inode number, this means that you can have another file name that maps to the same inode. The data structure of a file system allows you to do that. Right? The simplest example is that you can create a file A and the root directory, write some content to it, and then you can create a file B. But in this file B, you do not create a new inode and new file. You just see that this file B reuse the same inode. What does this mean? File name, file A and file B, they're just aliases of the same file. Okay, this is what hard link in file system. Right? You have different file names, but they are pointing to the same inode. Okay. The file system allows you to do that. Okay. Yes.
If I create a new file that points to the same file name that points to the same inode, and then you like remove the original, do I lose the inode as well?
Do you remove the inode? Do you really delete the file? Right? So that's what's written here, right? So you have a reference count, right? To keep the track of the number of file names that are really reference this inode, and you don't delete this inode until all the references are clear. Okay, yeah, so only when the reference count reaches 0, the file is removed. Okay. So this is called hard link. All right, and there is a downside, which is hard link cannot. Actually, let's first explain the usage. Right? Can you imagine what is the reason that we want to have these hard links? The motivation. Right? Do you see any examples of hard links on your computer? Yes.
When we're in a subdirectory and we want to go to the parent directory, we do like cd dot dot, which is an alias for like the parent directory.
One example. Any other example? Yes.
Like, for library management.
Exactly.
Environments and stuff.
Right. So both are good examples, right? So the common one is that when you install a software, right? When you install the software on your Linux machine, for example, and you will see that they are, when you use those software, you usually find that they exist in root directory, binary directory and a root directory. But they are really just links to where the binary, the real software is installed. Usually the software is installed in a separate location, and the binary directory is just a link to that installed software. Okay. Yeah, so it's easier to manage. And so that's one reason that we want hard links. The downside of hard link is that it cannot cross partitions. What does this mean? You can imagine that you have two partitions, or make it easier, you have two different disks. Each disk is formatted differently, right? Formatted independently. And they could have their own inode list, right? A list of inodes. And they could have overlapping inode numbers. Right? Disk 1 will have inode 0 as well as inode 100. Disk 2 will have inode 0 to inode 100. Right? So because the inodes across different partitions or different disks are not, they are managed independently. Right? So in one partition, you cannot reference the inode of another partition. Okay? I forgot about this. I think previously I used this example. Actually, you can try this. I try this later. I think yeah, I'm not sure what's this example for, because the current directory should exist in the same partition. Right? Yeah, maybe you can try it. So the point of this question leads to something called soft link. So this ln-s is saying that you're going to create a soft link instead of the hard link. Okay. So soft link is different. Remember, hard link is not a separate file. It's just two file names pointing to the same inode. Right? Every inode represents a file. Two file names pointing to the same inode, meaning that there's only one file. Just have two aliases, two different names. Okay. Soft link is different. Soft link actually has its own file. Okay. Right. So soft link is a separate file. It has its own inode, and this inode has some content. The content is special. The content is just a full path to the other file it's linked to. Okay. So let's see in this example, right? We'll create a link to this target file. And these two things, they are on different partitions. For example, I want to create this name link in the partition 1. This target file is in partition 2. Okay? In different partitions. Now, this name link, different from a hard link. This file is actually a separate file on disk. In the previous hard link, in that case, this won't create a new file. It will not allocate a new inode. But in this case, you actually create a new file. Let's say this is on partition 2, this is on partition 1. You are creating a new file on partition 1. It has its own inode and its own data block. The only thing that's stored in this data block is the absolute path to this target file in partition 2. Does this make sense? So it's called a soft link, which means that it's still a link. Right? Why? Because it stores the absolute path to this target file, so the file system can use this absolute path to find this target file. Right? When you access this file, this soft link, the file system will transparently redirect you to this target file using the path stored in this data content, stored in this data block. Okay, let's do a simple comparison. Right? So when you use if this is a link is a hard link, when you access it, what happens? When it's a soft link, when you access it, what happens? Let's try to explain this. Right? Think about this. Do a comparison. If you can make this comparison, then you understand the difference between these two. Suppose I created two. This is the same target file. I use ln to create a hard link. Right? Let's call it link 1. And then I use ln-s to create a soft link. I call it link 2. When I access link 1 and link 2, right? What happens? What's the difference? Give it a try. If you can understand it, explain it, then you understand the difference. Yes?
So with the hard link, it goes to the table and then gets name link, the entry, and then it maps it directly to the inode for target file. But then in the soft link, it goes to, so there's an entry for name link, but instead of pointing to that inode for target file,
goes to that path, you need to use that new path to go through this entire process again, right? Starting from root directory and then go right and look up for the every directory on this path until it reaches the target file. So that's right. That's right. So okay, let me repeat this, right? So if this is a hard link, right? When you use this link one, right? For example, link one to access this file, then once you reach this the file name of link, right? So you get this mapping from link to the inode of this link, right? That inode is already the same inode of the target file. Right? You retrieve the inode of the target file immediately there. And you get the mapping from link to that inode, right? Because they share the same inode. When you use when you use soft link, right? Then when you reach this mapping from a link to the inode is a completely different file, not the same as the target file. It's a completely different inode. You use that inode to read its content. The content is the full path to the target file, and you use this new path to redo the scan or the file system lookup process, right, to reach the target file in its partition to find its inode. Okay, that's the difference between a soft link and a hard link. Okay, all right. So opening a file, once you get to the inode of the file, and then you can use that inode to access the file. Right? So you keep track of open file inodes, and you also store the current read-write location within the file. Right? So for each file you can fseek, which is means that you adjust the pointer inside this file to some offset, right? And then you start reading or writing from that location. Okay. So these are APIs are constructed on the abstraction of stream or file stream, right? Or character stream. And in Unix, I'm not sure whether you're familiar with this philosophy, right? So everything is treated as a file, if you have heard about this. Everything is a file. And what exactly is a file? Right? Every file is just a byte stream, a character stream or byte stream. Okay, and that is a universal concept that is used in the Unix design. So a file is a byte stream. A device, right, is also a byte stream. Right, every device is also abstracted as a byte stream. So your network is also abstracted as a byte stream. Right? So all the objects inside Unix is abstracted as a byte stream. And that is the universal interface, and that is what makes Unix so simple and elegant. We found that using this file as an abstraction for everything makes the system design much simpler. Okay. So, yeah, data structures for a typical file system. Right, you have a process control block. Every process have the process control block, and this process control block stores the open files, files that are open for a process. Okay, and the open file table, I have a system-wide open file table recording all the files that are open. Okay, and this is also record which process has opened a file. Some file can be opened by multiple processes, and they are allowed to do that. And some files, if you set a protection, then it can only be accessed by one file. Okay, and this open file table, right, its entry has the mapping to, okay, this file, where is its inode, right? So this mapping helps you to identify the inode and use the inode to read or write the file content. Okay. All right. So per process table information. Right? So remember this. Right. This is process control block. Right. So every process need to remember the files it has opened. Okay. This is very obvious, and also information regarding the use of file by the process, and the allowing items may be stored on per file, per process basis. Right? Current file pointer indicating location in the file, read the write position, and right, so each entry in the per process table points to an entry in the open file table. Okay, so this is just to explain this. Every process has a control block. It remembers all the files opened by this process, and every entry points to a entry in the open file table. Okay. All right. So in the open file table, it has a list of open files, of course, and every entry not only remember a file that is opened, but also the file open count. Right? So how many processes that have opened and closed a file. Right? Track the number of opens and closes. Right? And also tracks the pointer to the inode. Right? So this is obvious. Okay. Okay. So another thing, very important topic, is file system consistency. Okay. The let's start with the difference between memory and the disk, right, to motivate the demand for file system consistency. Why do we want to learn about this topic? What is the difference between file system and memory? Yes?
Memory typically refers to the volatile memory where nothing's actually preserved, whereas the file system itself is going to most likely be associated with a set drive or partition where the data is running.
Mm-hmm. Exactly, right? So file system is usually managing external storage which has persistent storage, right? So it's able to persist data. But memory is usually referring to volatile, which if your computer crashes, it forgets everything and you start from fresh. Right? The difference is that if your computer crashes and restarts, right, everything in your memory is wiped out and you start from fresh, but things on your disk might be left corrupted if, let's say, some operation did not finish, right? If your computer crashed during the write operation, for example, right? If the write finishes, if some write operation only finishes in the middle, right? Finish half of it, then it might leave your file system or disk in an inconsistent state. Let's use the simplest example, right? When you modify a file content on disk, okay? What do you do? When you modify some file content on disk, you know, imagine what are the steps, what are the data structure that you need to modify. You may need to modify. For example, if you're appending some block to a file, you may need to modify the free block list on disk, right? Because you might need one extra block. Right? You need to modify the free block list to get this extra block, right? And then you need to modify the inode because you need to add this block to your inode, to that file's inode, right? And then you need to really write data, right? If you're appending the data, you need to write the data to that block. Right? These are the three most obvious operations that you need to finish during this write. Right? Modify the free list, modify the inode, and then write the content. If your computer crashes during this, right, in the middle, right, for example, after the first operation just removed, after it allocated a free block, and the computer crashes, and what happens? Right, you lost when you restart, you find that you lost a free block, and nothing is written. Right, this free block is not added to any file. It does not contain any content. It's just lost. It's just marked as used, but it does not appear. It did not appear in any files inode. Okay, very typical example of inconsistency. All right, so that's why file system management and memory management is very different, because file system manages persistent data. So after you restart the computer, if you haven't performed some crafted write before the crash, you can still see them, and this is an inconsistent state. Okay, and right, so during this kind of crash, the file system can be damaged, and you need to reconstruct the file system to restore it to a consistent state. Okay. So that's there are many different techniques to handle different type of crashes. Right? The simplest crash that I think is the one that we just mentioned. If the your machine crashes after a free block is allocated. Right? The simplest that's the simplest type of crash, and the approach to restore consistency is also easy. You just scan the free block list and find that, okay, there is a block that is not free but not used by any inodes. Let's just add it back to the free list. A simplest approach of crash consistency, restore the consistency of your file system. Right? That's one job of FSCT, which is file system check. Right? File system check does this kind of simple check, and it will find the free blocks that do not belong to anyone and then add it back. That's the simplest technique that is implemented decades ago. Right? Okay, but more advanced technique, right? Usually use journal file system. File system journal, which we'll explain later. Let me see. Yeah. Okay. Let's explain the simple technique first before we explain the journal file system. Right. So the simple technique, right, which FSCT does is that it will iterate through the blocks of files, iterate through the blocks on the free list. Right. So it can just scan them and check that whether the file is in one block, in either the some files inode or on the free list. Right? If there exists some block that does not belong to any of them, that does not belong to the free list, does not belong to any files inode, it means that there's some inconsistency. It detects that there is a problem. Right? This is very simple to check. Right? Okay. Missing block, right? So the previous example we just mentioned, if you found that there is a block that's not on the free list, also does not belong to any file, you just add it to the free list. Okay. Right. Free list has let me see. Yeah. Another example is that if you are really using a list, and somehow this free list has this block twice in this linked list, right? That's also wrong, and you just have to review the free list. Right? Of course, if you are using bitmap, you don't have this issue. Bitmap is not a list. You cannot have the block, one block in the in bitmap twice. Okay. Or you might also have a block present in multiple files. Then you can restore the consistency by allocate a free block and duplicate. These are some simple operations that is performed in FSCK to restore the consistency of file system. Okay. All right. Yeah. So the more advanced technique to guarantee file system consistency is a file system journal, which is the high level idea is that you log the operations that you want to perform, right, such as allocate a block from free list and then add it to some files, inodes, and then write content. Right, you log these operations before you really perform them. So when your system crashes and you come back, you will see where you are in these operations, and then you know where did you crash and whether you can restore the consistency. Okay, so we'll explain that technique in more detail in our next lecture. That's it for today. If you have answer questions, come up and write them. Thanks.
Trung has a shirt that says Hail Purdue and the AIs.
He got it freshman year. I'm so pissed that he didn't do that. I did not know about it.
What was it?
It's like some freshman syllabus. I wanted that shirt. I also forgot my umbrella in Boston, so I'm really hoping it doesn't.
Yeah.
For the rest of the day. Before turning
Okay, I got
Yeah.